Okay, class, remember it's Tie-Dye Friday. This lecture is meant to be for April 3rd. So let's continue right where we left off. This is a discussion of hypothesis testing, and I think it really brings us into a cool place with what we've learned so far with our descriptive statistics and our inferential, our discussion of inferential statistics with the central limit theorem. So let's just get up to speed from the last video. What we did here was we're giving people 4% sucrose solution. We're going to ask them to rate the sweetness of the solution using a visual analog scale. That's about 200 millimeters long. This number represents how far from the not sweet side they are rating the solution. And we set our criteria for our decision making, okay, in terms of our null hypothesis and our alternative hypothesis, okay? And we said, once we test these individuals and they taste the sucrose solution with the red food coloring, if the mean falls outside of what we expected, and what we expect here, we expect to see numbers in here. And let me clarify this, because this is where we expect to see the rating if the food coloring has no effect. Okay, so this is a little bit of a twist here, thinking about things. But take your time. I say that a lot, don't I? Take your time and think about it. If the red food coloring does not have any effect, if the red food coloring does not have an effect, we should see their ratings in here somewhere. That is, the subject should look like they're tasting a clear solution. If instead we have these people taste the sucrose solution with the red food coloring, if they rate it out here or out here, then we're going to say, hey, these folks don't look like the folks that are tasting the clear solution. Okay? That's the logic. We're given information about the clear. So in a way, what I'm asking is not whether the red solution looks different, but I'm asking, does the red solution, is that being rated like it was clear? Okay? It's the flip side of a coin. It's just like, when I say, am I taller than you or are you shorter than me? It means the same thing, but it's worded a little bit differently. So I want to see if the red food coloring ratings look like clear ratings. That's in a nutshell, okay? So we talk about alpha level. That's given by this symbol. That's alpha, okay? It's used in a lot of religious symbolism too. Symbology, wow. That is alpha and omega. It's the same letter, okay? We set the alpha level at 0.05. That means we're identifying the extreme 5%. 2.5% here, 2.5. Extreme 5%, this is the middle 95%. And then we're usually just going to write this for step 2. Once you get used to this, you won't be drawing this curve. It will be sort of an assumed curve in your head. When you tell the reader this, you're telling the reader that you're talking about this part of the curve. Alpha 0.05, a z of 1.96. Okay? So the next step, step 3, is to collect the data. This actually occurs at step 3, and we can talk about that in a couple videos to come, perhaps, if we have the time. But we're going to collect the data. So I'm going to have people come in the lab, and I'm going to have them rate the solution. And what I do, because I'm a good researcher, and I don't say that it's well, I guess it's my opinion, but I've been trained to do good research. The first thing I'm going to do is to test my subjects, is to test to make sure that they are not colorblind. Because if I give someone a red sucrose solution and they are colorblind to red, then it won't look red to them. So I haven't really done the experiment. Okay, this is another situation where, it may be that nobody told you to do that, but you have to think about what are the potential problems. About 10% of males are red-green colorblind. About 1% of females are. There's a gender difference there. It's a genetic trait. So about 10% of subjects are red-green colorblind. I don't want any of my subjects that come into the lab to taste this this red sucrose solution. I don't want them to not be able to see it. So that's the first thing I'm going to do, is test them for color blindness. Okay, they come in, I test them for color blindness, and find that they are good to go. Give them the sucrose solution in a clear cup, but the solution is red. Now, a little side note here. Food coloring has no taste, okay? It is formulated so that it has no taste. It's just the color, all right? So I'm going to give them the red solution. They taste it. I'm going to have them spit it out because I don't want them to ingest the solution. I just want it on their tongue. So they taste it, swirl around, spit it out. Then I give them the visual analog scale and have them write, put an X in terms of how sweet they think it is. Okay. I don't want to do this with just one person, because one person can be average, they can be above average, below average, or they can be pretty weird. In other words, this is where I'm really putting the central limit theorem to use. So I want to know how people will rate this red solution. When I say I want to know how people will rate it, I really want to make a conclusion, a generalization, based on anybody coming in and tasting that solution. Okay? So the mu here, the population, that canvas bag, is really anybody, millions of people. Okay, how would they taste it? So instead of using one person, I'd rather use a sample of people. 2 is better than 1, 5 is better than 2, 15 is better than 8, and so on and so forth. This is hopefully redundant from what you remember. So let's have 8 people come into the lab, okay? So 8 people sign up for the experiment. I mean, maybe 9 signed up, but one of them's colorblind. I don't want to use that person, okay? So 8 people show up. I look at their visual analog scale ratings, and this is what we find, let's say, for example. So for my 8 subjects, that means I have a sample of 8. The mean rating for this red sucrose solution is 70.25. And again, this is we're making pretend that this is data that we've collected in the lab. That's where these numbers come from. They come from people rating on the visual analog scale. Okay? And so what I want to do now is I want to compare this mean, right? I want to compare this mean to what we would see if people were tasting clear sucrose solution. Aha, but here's the issue. We have the information from individual people tasting clear solution, but I'm not going to compare my sample of 8, this mean, to individual scores what I need to do is I need to convert this distribution of individual scores to a sampling distribution of means for the clear folks. Okay? This is the color. This is the red solution. This is clear. But I want to see if the red sample looks like what a clear sample would look like. I want to see if this looks like what a clear sample of 8 looks like. But these are individuals, okay? So let's do the conversion. I like to do it this way, just like we've done before, except it's not curved this time because I have to make room. Okay, this is the central limit theorem. Central limit theorem. So then this ends up being my distribution of sample means. Oh, I'm so glad I tightened up this easel. The last video was kind of falling down a little bit. These are sample means for the clear solution, okay? Sample means for a clear solution. But we know what that's going to look like, right? We know that the mean here will be 80, right? Because we know central limit theorem, the mean of a sampling distribution of means will equal the mean from our individual population of individual scores, okay? We know that. Awesome. And I also know that the sampling distribution standard deviation, otherwise known as the standard error, will get smaller based on the original standard deviation. And we're going to divide by the square root of n. Okay? So let's do that. My standard error in this case is going to be 12 divided by the square root of 8. 12 divided by the square root of 8, and I did the calculations. Here they are right here. And so my standard error is going to be 4.24. Okay? If you remember from the last video, and you can take notes on these videos, you can watch the video again. Here's a distribution of individual scores. This is for the clear, okay? There's a mean of 80, standard deviation of 12. I'm going to convert that. This would be all samples of n equal 8. This would be all samples of n equal 8. This is for the clear. What I want to do is I want to compare my subjects that are getting the red sucrose solution. I want to compare them to clear, okay? This distribution will have a mean of 80, but the standard deviation of this sampling distribution of means will be smaller. Divide by the square root of n, divide this standard deviation by the square root of n. We have a new standard deviation for this distribution. It's also called the standard error, and that's 4.24. But I'm going to use this criteria. Absolutely, I'm going to use this criteria. It's just now I'm comparing samples to samples instead of comparing scores to scores, sample to sample. And I certainly don't want to compare a sample to individual scores. That would not be cool. Everything is on this distribution now. I'm still going to use z-score of plus and minus 1.96. I'm still going to use that as my criteria to make my judgment. Okay? So step 3, we're going to collect the data and we will do the computations and I'll show you what that looks like. Here we go, okay? I want to get my z-score for my sample of people that are tasting the red solution. I want to compare that to what samples that taste the clear solution look like, okay? And so if I do that, let me go this way and make it easier. Hoping everybody's good with this conversion, okay? So, here's the formula, all right? So I'm going to take my sample of people tasting the red solution. I want to see if they look like samples of people tasting clear, right? Pay attention. Just don't just plug the numbers in to the formula. I'm comparing my red group to my clear group, okay? I'm asking, does this look like this? Does this look like this? Or is this close enough to this so that I can say, hey, it looks like they're tasting clear, all right? Or is this far enough away for me to say, wow, I think the red food coloring makes a difference, okay? In this case, divide by 4.24. This becomes the z-score for my red sample, okay? And let's do this calculation. I'll let you do that with your calculator. I'm going to take a little sip of water. And what we have with our z-score is a z-score of negative 2.30. Negative 2.30, okay? Pretty good. I'm going to go back here. Here's our cutoff. We said anything that is above 1.96 or below negative 1.96, either of those options, we're going to say, gee, that looks kind of weird. That's not what I expected. Here's the 95% expected. Here's the weird area, okay? It's weird. And so we have a z-score for our red solution people. We have a z-score that's negative 2.30. So that's down here somewhere. Wow. Okay, so this is our step 3. Collect the data, calculate the z-score. Okay, collect the data, calculate the z-score. Step 4 is now making sense of this. Okay, well, what the hell does this mean now? All right. Well, let's think this through. Take your time. Did I say that again? Of course I did. Okay. Take your time. Let's think this through. People that are tasting a clear sucrose solution rarely rate it as low as 70.25. That is, in terms of a sample of 8. Just like they would rarely rate it up here. So it looks like the people that are tasting this red solution, they don't look like they belong to this distribution. Could they belong? Yes, they could, okay? Anything can happen. We're not talking about possibilities. We're talking about probabilities in this case. But I'm thinking to myself, this would be a very weird sample of 8 for people tasting clear sucrose, okay? And so I need to make an experimental decision. Let's go back to our hypotheses. Okay? We have two hypotheses. We have to decide, based on our data, we have to decide which one seems to be true. Okay? If the population of people drinking red solution has the same mean as the population drinking the clear solution, we should see the red solution be somewhere around 80. Okay? That is for the ratings. The alternative in this case is that the red population, people drinking red solution, is different than what we would see for clear. In that case, we would expect that the red food coloring group is going to have an average rating different than 80. Okay? And so step 4, we can do it right here. I think it's a good place to do it. Step 4 is to make a statement about the null hypothesis. We're going to make a statement about the null. We're going to make a statement about the null hypothesis. It's always about the null. If we think about our three-legged cow, that gives you an idea of why that is. I can't prove my experimental hypothesis. What we're going to work with is trying to disprove the null. Okay? So based on our data, that is, that our red food coloring group would have a z-score of minus 2.30, our red food coloring group, if that group was on the clear distribution, on the null distribution, okay, it would look very weird. And so I don't think that this is the case. I actually think that the red food coloring is making a difference. I don't think that this is the case, okay? It doesn't look like the red food coloring group is rating the solution in the same way that the clear group would rate it, okay? So we have two possibilities for our decision about the null here. We can either reject the null hypothesis, okay? That's one of the possibilities. We can reject the null hypothesis, or we can fail to reject the null hypothesis. We can either reject the null hypothesis, or we can fail to reject the null hypothesis. This oftentimes gives students fits a little bit because we're actually dealing with a double and a triple negative. But again, I will ask you, I will plead with you, please try to take your time, okay? Every one of you is capable of thinking about a double negative, okay? Every one of you is. It's just you have to take your time. Everybody's in such a rush. Suppose that I said to you, I'm not going to go to the grocery store today. I'm not going to go to the grocery store today. Do you think I'm going to go or not? And of course you would say, yeah, of course you're going to go. That's a double negative. I'm not going to go to the grocery store. That means I'm going to go. All right? Same thing here. We can either reject the null hypothesis. What does that mean? I'm rejecting the notion that these two groups are equal. Right? If I reject the null, I'm saying that I don't think that they're equal. All right? If I fail to reject the null, then that means it looks like the two groups are equal. Excuse me. So in this case, what do you think we're going to do? Reject the null or fail to reject the null? Our sample was at a z-score of 2.3, negative 2.3, okay? So in this case, we're going to reject the null hypothesis. We're going to reject the null hypothesis. I'm going to say, I don't think this is the case, based on the fact that if this were the case, I would expect the z-score for my red group to be less than 1.96 or greater than negative 1.96. I'd expect it to be in the middle. In this case, it certainly wasn't. So I am rejecting the null hypothesis. I am rejecting the null hypothesis, okay? Which really means that I think, if I reject this, then this is my only alternative. Remember I was talking to you about why it's called the alternative? We make decisions about the null. That's what we're going to do that every time, folks. If you want to memorize something, memorize that. Your decision, we're going to make a decision on the null, okay? So in this case, we reject the null. I'm rejecting the notion that these are equal. So that means, looks like they're different. Okay? Step 1 through 4. I always include a fifth step. In fact, I don't think that the book formalizes a fifth step. For me, the fifth step is just as important as the other stuff. I mean, this is the statistical analysis, but I do want to make a report. I do want to make a conclusion in my research article that I'm submitting for a conference or a publication or whatever. So let me get a blank sheet of paper and I'll show you. This is the statement that we're going to use, and it'll actually clear up some confusion that you may have. If any of you have been reading journal articles for science courses, biology or psychology or others, I'll show you something that hopefully will be enlightening. Okay, so new sheet. So this is where I'm going to write my conclusion. I've done the research. I'm a good researcher. I made sure that people weren't colorblind. I made the red sucrose solution so everybody gets the same red. I'm having them rate it on the visual analog scale. And now I'm going to make my conclusion. Okay, so here's what we're going to do. It appears that addition of red food coloring significantly, ran out of room there, but that's okay, significantly decreases because my ratings were lower than 80, okay? We'll talk about this in a minute because this is a surprise. It appears that addition of red food coloring significantly decreases ratings of sweetness. Okay? This is not my opinion. This is the good thing about science. It doesn't care what my opinion is. And in fact, I thought red food coloring was going to increase the sweetness ratings. I use this example specifically for a couple of reasons. Number one, this is what actually happened in our lab. And in fact, I didn't at first believe it. And I'm like, what? I thought putting red food coloring in would increase sweetness ratings. This is weird. It doesn't make any sense. That is the worst thing that I want to hear from anybody doing science. Oh, this doesn't make sense. I mean, the data will tell you the truth. The data will tell you the truth. If it doesn't make sense, that must mean that I was not thinking properly about how this would work in a taste situation. But I want to make sure that people know that it's not just my opinion, okay? That we actually collected data and that it's the data that are telling us this. So I'm going to put a justification in here in parentheses. And by the way, one of my pet peeves is people don't understand that parenthetical information is part of the sentence. A lot of people want to put a period and then put parentheses. I'm like, no. The parentheses is part of the sentence. So I'm not going to put a period here because I'm putting in some parenthetical information. I want to justify why I'm saying this. This is not my opinion, okay? So I'm going to tell the reader, I'm making this statement because I had a z-score of 2.30, and in fact, it was a negative 2.30. That's why I'm saying it decreased. Of course, I just looked at the average for the group. It's 70.25. The average for clear is 80. Okay? Then, and I'm going to ask you to do this on the exam. Of course, this is what we do. Okay? Then a semicolon. And now some terminology that you may have seen in, if you're reading any research articles, you may have seen this. I'm going to put lowercase p, less than 0.05. Now I'm going to put my period, okay? So this is step 5. Make your statement. That is, report your results, okay? This is the fun part. You've done all the work. Now report our results. It appears that addition of red food coloring significantly decreases ratings of sweetness. This is why I'm making that statement. So this justifies it. In a way, this is saying, hey, it's not my opinion. We did the research, okay? Very powerful. And we've put all of the information that we've learned into this hypothesis testing procedure. And it's very powerful, I think, because I think I said this in the first week of class. I mean, everybody has a right to their opinion. I'm opinionized, you're opinionized. When we're doing science, when we're doing medicine, when we're doing therapy, I don't want it to be based on just people's opinions because they may be wrong, okay? We collected the data. There's empirical evidence to make this statement. And here's how I'm encapsulating it. All steps 1 through 4 are steps that you never see. This is what you're going to see in a journal article, okay? It's important to do steps 1 through 4 to get to this point, but here's the conclusion, okay? Now, before I talk about this a little bit more, I want to talk about our lab. When Stan Hewlett came in and said, I want to put red food coloring in and then see if it affects people's sweetness ratings, we both thought that it was going to increase sweetness. And we were both wrong. I didn't believe it at first. We redid the experiment the next semester. We found exactly the same thing. Now I could say, this doesn't make sense, this doesn't make sense. But instead, because I'm not only a good researcher, but I try to be a good scientist, I asked myself, why does this make sense? Why does adding red food coloring decrease people's rating of the sweetness? And after I did some more reading and I talked to some people about it, it actually makes a tremendous amount of sense. When I give you a clear solution to taste, even if I say this is a sweet solution, taste this, you really don't have any expectations. It's a clear solution. I don't know, I told you it's going to be sweet, but how sweet? So there's no expectations. When I say I want you to taste this solution and you look at it and it's red, like Kool-Aid or Mountain Dew, or Hawaiian Punch or whatever the hell red drink you're drinking, When I give you that red solution, you actually have an expectation that it's going to be sweeter. So here are the two situations. Clear, no expectation. So you're sort of rating the sweetness of the solution sort of raw. So we get a mean of 80 with some variability, of course. When I give you a red solution, you have some expectation that it's going to be sweeter, so that when you taste it, you know, there's a little bit of a letdown, or you're comparing it to what you expected, and so you're actually going to rate it as less sweet. And in fact, we've done this in the lab before. Your expectations about what you're going to taste can really influence how you taste something, okay? So it's like, yeah, all of a sudden it makes sense. Well, it has to make sense. These are the data, and we replicated this, and so we have to figure out why it makes sense, and we did it. It was kind of cool. All right? I want to go back to this. This is really important here, okay? This p less than 0.05. Of course, it's a probability, p. It's telling me the probability of something is less than 0.05. This is how it's written. This is how you will read it in journal articles. But I'd like to do this. I'd like to say the probability of the null hypothesis is less than 0.05. That's sort of a quick and dirty way to think about it. The probability that the null is true is less than 5%. Okay? And there's a reason for that. I'm going to go back here. Okay? Oops. Where am I at here? I'm going to go back here. Here's where a red sucrose solution is. Here's the sampling distribution of samples of 8 that are tasting the clear. Okay? What I'm saying here is this doesn't look like a clear solution group. It's too far out. It's too low to look like a clear solution group. It's like when we're flipping a coin. You know, when I get to 80 heads and 20 tails, that just doesn't look like a fair coin. But I can ask this question. Could it be fair? The answer is yes. Whenever I say could, I'm talking about possibilities instead of probabilities. This doesn't look like a clear group. Could it be a clear group? That is, could it be the case that the red food coloring really doesn't make a difference? The answer is it could. The chance, so this is a more extended version for that p-value, the chance that you would get a clear group out in this area, the chance that you would get a clear group out in this area is less than 5%. Okay? So maybe the red food coloring doesn't really have an effect, but boy, that would mean that we just got a really, really, really weird sample of clear. So I have a decision to make. Do I think something really weird happened, or do I think that the red food coloring made a difference? I'm going to go with, I think the red food coloring made a difference. But if you notice this word, and I always start my conclusions with these words, we'll do another example on Monday, the next installment of the video. We'll do another example from start to finish, all 5 steps. It'll be in the same format. Okay, we'll probably do 2 examples, and I'll show you it's like the same format every time. I'll make sure that the decisions are not the same. But I always start with, it appears that, it appears that, it appears that, because ultimately this is a probability statement, okay? Even when I have these data, it could be that I made a mistake. But I think less than 5% of the time, I made a wrong decision here. So that's pretty good. I mean, I'd like to be that confident most of the time. With all my decisions, that is. It appears that the addition of red food coloring significantly decreases now ratings of sweetness, okay? And if I wanted to, I could put ratings of sweetness of sucrose solutions or something like that. You can make this a little bit longer, but this is the essence. One of the things that people do sometimes that I don't like is they'll say, adding the red food coloring made a difference. And I'm like, what kind of a difference? What kind of a difference? Because it could have increased the sweetness ratings or could have decreased the sweetness ratings. Make sure that you talk about the results, what you found. In this case, we have a decrease. Here's my statistical analysis. Another thing that people will make a mistake every time I give an exam like this, they'll put a Z of 1.96 here. No. That's your decision criteria for sure. Those are the lines that you use to make your decision. I'm reporting my results here. I'm reporting my results, okay? So this is my Z-score for the red sucrose group. And then this tells me that the chance that the null is true is less than 5%. The probability that we would get a clear solution with this Z-score, the probability that we would get a clear group with this Z-score happens less than 5% of the time. So my conclusion, my inference here is that the red food coloring made a difference. Okay? Steps 1 through 5. Set up your hypothesis, step 1. Step 2, make your alpha level. Report what Z-scores you're going to use for the alpha level. Step 3, do your statistical analysis. Collect the data and do your statistical analysis. Okay? Step 4, make your decision about the null hypothesis. Step 4 is making your decision about the null hypothesis. It has to be about the null. You either reject the null or you fail to reject the null. Okay? And then step 5 is your report. This is how you're going to report out your data in your journal article or in a presentation at a conference or something like that. Okay, well, this is the end of week 2 of our online journey, and I hope, once again, I hope everyone is heeding the precautions of our healthcare professionals and the CDC. Please take it seriously, folks. There are some people who are starting to, have parties or play basketball or something like this. We all need to take care of each other. This is kind of an invisible thing that we're dealing with, this virus. So please heed the precautions and keep everyone safe. I have a little treat for you guys. Maybe, I hope you consider it a treat. I'm going to play a little song for you on my guitar. What do you think about that? Okay, so we'll put that there. We've had enough statistics for the week. So this is my baby. This is my baby guitar. And this is a song that I wrote. I don't write a lot of songs, but this is a song it's the first song I ever wrote. It was probably in high school. And so it was when I was young. And this is called Young, but the psychology Young with a J, J-U-N-G. So I'm going to play this and hope you enjoy it. stay safe, everyone, and enjoy statistics, and be good to each other.